Welcome back to the course in Nuclear Medicine Physics. Today we're looking at in vitro radiation detection. Unlike taking a scan of someone where the radiation is inside the person, in vitro refers to measuring the radiation inside someone outside of their body. We'll look specifically at two types of radiation detectors: the well counter, which we've talked about in previous lectures, and the liquid scintillator, which is a really interesting design. In addition, we'll pay close attention to the efficiency of different types of detectors. For example, if you have a small detector and you're detecting radiation emitted from a substance, only a small part of that radiation is actually reaching the detector. This type of radiation detection is used all the time in modern nuclear medicine, so it's very important that we get a good understanding of exactly what's happening.
Okay, hi everyone. One more lecture of our nuclear medicine course. Today we're gonna start talking about in vitro radiation detection. So I'm gonna jump over this real quick. My slide moves. Okay, so in vitro radiation detection. So when we do in vitro detection, it has multiple applications in nuclear medicine. And I give some examples here on the left. Shilling test, which is something that deals with measuring, I think it's vitamin B on a patient, or the blood volume. We can measure protein and fat absorption, the ferrokinetics. They're also doing immunoassays. And we can start asking questions like, what is the amount of radioactivity compared to a standard solution? And in some of these tests, radiation is administered to the patient, and in some others, it isn't. As we remember back in the days, on our first lecture, we gave some examples of that. And for this, the choice of detector is very important. And one of the big parameters here is something that we call efficiency or sensitivity. So the more efficient or the more sensitive your detector is, then that means that we can either reduce the radiation dose that we give to a patient, or maybe we can just count our samples for much shorter time. So what is efficiency? And efficiency for this in vitro detection, and mostly, but it involves two terms. One that has to do with the geometric efficiency, which I'm calling here by epsilon G, and one that has to do with the intrinsic efficiency. So that's basically of the radiation detector itself. So one, the geometric efficiency, we're going to see in a moment, is in the way in which you build and what type of geometry you put to these detectors. And the intrinsic is just because of the type of crystal or the type of gas that you are using to measure. And both of them combined give us like the system efficiency. So let's start talking about intrinsic efficiency, and how we define intrinsic efficiency is basically the number of events that interact with the detector divided by the number of total events reaching the detector. So again, you have a source. This source emits many particles. Some of them make it to the detector. We're going to count only the ones that make it to the detector. And from those that actually make it to the detector, we want to see what's the fraction that actually interacts in the detector. Some of those can just go straight without interaction. We want to see how many of those interact. So the intrinsic efficiency is going to have a range between 0 and 1. It's going to depend on the type and energy of the radiation. And of course, it depends on the attenuation coefficient and thickness of the detector. So the higher the attenuation coefficient for those particular type of emissions, then we're going to think, okay, that higher the chance of these particles interacting in the detector, then the higher the efficiency. If you think about a point source located on the central axis of that detector on the gamma ray, then you can think that it follows an equation like this that depends on x and the mu, the linear attenuation coefficient. That remember that attenuation coefficient is dependent on energy, so that's what I'm saying, just being explicit that mu value is a function of energy, but we can express it with a function like that. So if we look at a plot of the intrinsic efficiency, on the x-axis we see the energy of the different gamma rays reaching a detector, and this graph is taken from the Cherry book, Physics in Nuclear Medicine. what we see is that the thicker the detector, that is more efficient. Well, at low energies, it doesn't matter too much, but as the photon energy starts increasing, then you'll see a drop of efficiency for thin detectors. And let's think why that's the case. So if you have a very thin detector and you have a very high energy photon, then this photon is going to have a short probability of interaction. The material is not thick enough, so it might just go straight without interacting. But as you start adding and adding and adding material, so basically going up this curve, you are basically increasing the probability of interaction because, of course, now we are putting more of this material. So in that trajectory of the particle through this detector, is going to encounter more of these atoms, which it can probably interact with. So that's why it becomes more efficient. Now, what is geometric efficiency? And the geometric efficiency can be seen as how is that detector intercepting the radiation that is coming from the source. So it's going to be determined by the detector size, and it may or may not depend on the distance from the source to the detector. So we define an equation. We'd like to put a formula on this. The geometric efficiency is the number of events interacting with the detector, but look at the denominator. It's a little bit different than what we had for the intrinsic efficiency. Now is the number of total events emitted by the source. So now it's not only the events that reach the detector, we're now talking about every possible particle, every possible event coming out from the source. How many of those actually interact with the detector? So you can think, if you have a point source, for example, that point source emits radiation isotropically. So it emits the same amount of radiation in every direction. And we can think that we define the intensity of that source as being the emission rate of the source, which I'm representing with letter, I think it's called theta, I don't remember right now. And it's divided by the area of the sphere. So emission rate of the source divided by the area of that sphere. The area of a sphere is given by 4 pi r squared. So we can see that the flux decreases as 1 over r squared. And this is what is known as the inverse square law. This one is important, of course, for the detection efficiency, but it's also very important in terms of radiation safety. And something that we're gonna see as we go is, we know that the dose to a patient or the dose to staff decreases as 1 over r squared, and it's exactly because of this. So one of the ways in which you can think about radiation safety is you want to stand the further away as you can, the furthest away that you can from the source, and that's going to reduce that dose to you because exactly this sphere. So you can think that you have a detector of area A located at a distance r from a point source. Okay, so you have the point source and you're going to be standing at a distance r. So what we're trying to see is, if your detector has an area A, it can be your detector of area 1 or your detector of area 2, how much of all the radiation coming out of that source is your detector intercepting? So you can think, okay, if my detector has an area A, but the total surface area of that sphere is given by 4 pi r squared, then the fraction of that total sphere that my detector is intercepting is A over the total area of the sphere. Now, this is a good approximation for a point source when you have a point source, or you can also think about a point source being when your detector is very, very, very far away from the source. So when that happens, then your source just basically looks like a point. So I have a question for you. Let's try to think. If you have, for example, this detector, you put your source is here and you just have a little crystal that you put on the right. What do you think is the maximum geometric efficiency for these detectors shown here?
You can share the poll.
Yes, I'm trying. Oops. Okay. What would be Okay. So again, just try to think, if you put a detector on the right, the best that you can possibly measure is what? It's gonna be 1, 0, 5, 0, 25, 0, 75. I'm gonna give you 20 more seconds. Okay, let's stop that poll. So I'm gonna show the results. And well, the results are very divided. Most of the people said C, which is 0.25, but let's think. Okay, the correct answer in this case is actually A. But let's try to think why. And I'm just gonna make an exaggerated. Okay, so let's say this is our point source that's emitting radiation everywhere, isotropically. So the best case scenario that I have is, for example, when I have a detector placed on the right, and hopefully all the particles that come there will interact. But the reason that it's only 0.5 is because no matter how big my detector is, let's say we're able to capture all the photons that are traveling to the right, it's just going to be impossible to capture the photons that are traveling to the left. They're just going away from the detector. So at most, in the best case scenario, we're only going to be able to detect half of all the emissions coming out from that source. So that's why in terms of geometric efficiency, in a detector that's flat that we can put on the side is maximum 0.5. There is a question on the chat that it says, okay, how can we measure the number of total events emitted from the source? And that is a good question. So when we measure efficiency, and we'll see it later when we measure the efficiency or sensitivity for, let's say, for a SPECT camera, when we're trying to see what is the efficiency of a detector, we need to have a source in which we know very well what do we have in that source. So let's say you know very well what is the activity of that point source. So because you know well the activity, you know how many emissions are coming out of that source per unit time. So you do know very well what is the total number of emitted events from the source. And then you place this source in the detector, you go and count how many of those particles that you know were coming out of that source, because there are methods to measure very accurate activity. Then you go and see how many were detected, and you can calculate your efficiency. Yeah, so maybe, well, yeah, so someone's saying that what is the maximum efficiency of the 3 detectors shown on the right? Yeah, I guess maybe it's not fully clear, but what I meant is, at most, if you have detectors like this, at most, you cannot be more efficient than 0.5 because of what I just described. So if we have a smaller detector or a detector that is, okay, sorry, I just need to point at this. If you have, let's say, these detectors that's a bit smaller than this one, well, this detector you can expect to be slightly less efficient than this one because of the area that is being intercepted. But in the best case scenario, you cannot go more than 0.5. So you can just think if R is infinite or if R is very small, the best case scenario is 0.5. Okay, but yeah, so maybe I'll try to make this question a little bit better.
If I may make a comment, this very observation that if you bring the source very close was actually something used by the lab of Dr. Simon Cherry, where I suggested the idea of imaging very small animals by literally attaching them to the detectors. So by doing that, you bring up the efficiencies and the sensitivity significantly higher level. Of course, it's very specific to small animal imaging, but it's definitely a really key observation that you could bring up the sensitivity significantly by just literally doing that.
Okay. An equation that is more appropriate for closer distances, like when basically when the source is not fully a point source or the detector is not too far away, is something that looks like this. You want to see, if you have your detector, what's the angle that's covered between the source and the detector, and a geometric efficiency can be more approximately by this equation. So let's see when is this applied, and there are some types of detectors that are called well-typed detectors. So basically, you have a detector, you have a hole on it, and you're able to place your source inside the detector. You can think of the detectors typically, for example, when we talked about the dose calibrator. The dose calibrator was what we call a well chamber, because it has this concept. And that dose calibrator had some gas in these regions that then ionizing radiation will create the ions in that gas, and we're going to be able to measure some electric pulse. Now, we have some similar idea, similar concept. You have a well-type detector, but if instead of a gas, we placed a scintillator, so for example, sodium iodine, so now it's an organic crystal, because of the characteristics of, it's a higher density material, higher Z value. So the probability of interaction goes up. So putting a scintillator material there instead of a gas makes the detector more efficient. But when we think about this, when talking again about the geometric efficiency of the detector, when we place this, what we see now is that this cosine of theta, instead of being what I just see, it will be, for example, less than 45 degrees. Now, what we can end up covering is we have all this big angle here. So 0 degrees, 90 degrees, it's going to be almost 180 degrees. And in situations like that, you can reach a geometric efficiency that is closer to about 95%. So it's very, very useful to detect as many events. You're basically trying to imagine, like, the best case scenario is if you were able to put a sphere around encompassing all your source. So that's what we are trying to do. And well-typed scintillator detectors are trying to do that. You try to cover the maximum angle, just trying to intercept that sphere which that source is radiating for as much as you can. Yeah, and this is what I was just saying, that cylindrical hole that is cut in the middle of the detector, and the source is just placed very close to the center of the crystal. Now there's these machines that I'm showing here, they are called gamma counters, and they're basically well-typed scintillation detectors. But the way the reason that they're very useful is because you're able to put racks of test tubes. And so let's say, for example, you take many samples of blood, many blood samples of many different patients, and instead of just manually putting one sample in the well counter and then taking them out and then put the next sample, what this machine does for us is that it does it automatically. So it basically takes a test tube, it brings it into the well counter, it counts for some time, it removes, and then it grabs the next tube, and then you can just go and collect the result of how many counts did you get in each of the tubes. But the way it works is basically a well counter, and it's a scintillator that it's detecting those events. There's this thing called dead time, and so ideally, what you have to think about this is, if you have some count rate reaching your detector, then you should observe that count rate. So I don't know, for example, if you collect 10,000 counts per second are coming from your source, then you should be observing 10,000 counts per second. If you have 2,000 counts per second, 20,000 counts per second, then you should observe that same. The issue is that as the count rate starts increasing and it keeps increasing, you start losing some of the counts, and you start getting behaviors that look more like, okay, the ideal scenario is this blue line, which is the identity. The count rate coming out from the source is the same that you observe, but as the count rate start going higher, you start seeing more the red and the black behavior. So you start, okay, here you, for example, had 20,000 counts, but you're only detecting 10,000. So there's some counts being missed. And the reason for this is that the electronics take some time to process these events. Also, the scintillator takes some time to decay and come down to the ground state to be ready to emit some more light for new events. So in that time, that's why it's called dead time, it's like the detector is not really responding. So we're losing counts at very high count rates. This is also one of the graphs on the book. Ideally it goes like this, and the well counter behaves like that. So you need to keep in mind that, because there might be some corrections need to be made for these events. If you put a very, very hot sample, a very high radioactive sample, then you're going to be losing some count. So that's something that needs to be taken into account. So that's well counters that use scintillation detectors, scintillation crystals. The other type of detector is the liquid scintillator detectors. Again, we talked a little bit about this in the previous lectures, but these liquid scintillator detectors are used to detect beta or alpha particles. Now, because beta and alpha particles have very short ranges when they travel in matter, then they might get absorbed in the they will get absorbed in the radioactive sample by itself. Or if they actually ended up making it to the entrance window of the detector, then they might just interact with the window and not really be detected. So there are two options to try to deal with this. Either one, we create a very, very thin sample and detector with very, very thin window. So the very thin sample will avoid that radiation interacting within the sample by itself, or having a very, very thin window of the detector then will allow to not interact. I mean, will reduce the probability of interaction in that window, and the particles will be able to reach the detector that's behind the window. Or the other one, which is what I'm showing here, and is kind of the most efficient one, is we can mix the detector and the sample together. So we're going to have some liquid, we're going to put the radioactive substance there, and we're going to mix it. So we mix that sample with the liquid scintillator, and we place it inside a plastic or glass vial. So that's going to emit some light, of course, because of the interactions. But then what we can do is we're going to place that vial in between some photomultiplier tubes, and then behind these photomultiplier tubes, there's of course all the electronics like the preamplifier, the amplifier, and those electronics that we've discussed in previous lectures. And we're going to start counting what is the amount of light that is coming out of that vial. And that's a way in which beta emissions and alpha emissions can be counted. Now, those solutions have 4 components. It has an organic solvent, which is what dissolves the scintillating material and the radioactive sample. So that's what mixes the two. It has a primary solute, which is what emits the light when it absorbs energy from the solvent. So that's what's causing the light emission. Now, sometimes there's something called the wave shifter, which is basically a secondary solute. So this is typically being added to absorb the emissions from the primary solute, but then it re-emits light in a wavelength that is more suitable to be detected by the photomultiplier tube. So if we don't like the wavelength of the primary solute, maybe it's not very easy to be detected, or is not as efficient, or our detector is not as efficient for that particular wavelength, we can add this wave shifter to just have emissions of something that can make it easier to read. And then there can be some additives, and that's just basically to improve some of the performance, like, for example, I mean, something that can help the blood samples dilute better in that solution. Well, I mean, it's common to use these scintillator detectors, these liquid scintillator detectors, when we measure compounds labeled with tritium or carbon-14. And in medicine, again, we use it to count biological samples like blood samples or urine samples. The drawbacks is that they are very inefficient for gammas and X-rays, because this solution is made of a low density, low Z material. So it's very close to water, let's say, but so it's not as efficient as, for example, using sodium iodine. So here, the light output is basically 1/3 of that if we were able to put an organic crystal. And that coupling between the vial and the photomultiplier tube is not the most efficient. So yeah, so that's a drawback. And yeah, so preparing the sample might sometimes need some spatial preparation. and think that the sample is destroyed. So once you mix this radioactivity with this scintillator, then it's not very easy to open. Yeah, you basically won't be able to extract just that sample that you put into that solution. Yeah, here are some more drawbacks. There's this quenching, which is the reduction of amount of light output. The chemical quenching, for example, is there will be substances competing for the absorption of the energy from the solvent. So we ideally want this energy to be absorbed and released by that scintillator material, but maybe oxygen is also in the sample that will be taking some of these, that is going to be taking some of these emissions. The color quenching is, for example, if you think on a blood sample and blood is red, so maybe some of these emissions are going to be just absorbed by the blood itself instead of the scintillator, or instead of actually making it all the way to the photomultiplier. So the sample itself, what you put in there, might also end up just blocking some of those emissions. And the dilution quenching, which is relatively large volume samples, is added to the scintillator solution. So this reduces the concentration of that primary and secondary solutes, and it reduces the efficiency. What I mean with organic solute, I think, okay, what I mean with the solute is what is going to be able to dissolve your substance in this liquid scintillator. And the other thing that I was saying is the organic crystal, which, for example, sodium iodine, but that's a solid crystal. This is an inorganic crystal. That's what I meant. Is just a solid crystal, so the Z and the density is higher, so it's gonna have a much better efficiency compared to this liquid solution. I think that's what you're asking. Yeah, so this is just the techniques that we use for in vitro detection. Basically, the ion chamber, which, for example, a dose calibrator, but we use only that to measure radioactivity, is a gas chamber. If we replace that gas for an inorganic crystal like sodium iodine, we improve the efficiency and we make these well-typed detectors that are very, very efficient. And yeah, and then if we need to count betas and alphas, we just put these in some liquid that emits light. So that's everything that I have for now in terms of in vitro detection. That's a very short lecture, and now I'll give the floor to Arman, which is gonna show you some other slides of a slightly different topic.